nothing. We have to start all over again. X equal to 0, 0. Okay. So very much the same thing. The only difference is that, as you can tell, C is a function of state and input. In the board machine, C was only a function of state. So that's why we had to find out equations. So here, for the block diagram, the difference is that, again, the number of flip-flops is the ceiling function of number of states. Everybody knows the ceiling function from 28, whatever. So we have three states. Ceiling function is smallest integer, which is greater than or equal to this. Smallest integer, log 2. Sorry. It's a log 2. Log 2. So smallest integer greater than is 4, log 2 is 2. So that means we need 2 states. 2, sorry, not states, 2 filters. The number of flip-flops is log 2 of number of states. Okay. So that's 2 flip-flops. So we're going to require 2 flip-flops. Q, D, Q1, Q2, D. We're going to have a next state generator just like next state generator. The various things are the same. 0, 1, Q0, Q0, Q1, then plus the X, and then for the output, it requires state and input. So not only X goes in there, but also the Q's go there. So then we'll just draw this one in blue. So that's the only difference between the two. X. So the neat board did not have X going into there because output depended only on the state. So this is the output generator. And then we have the clock and reset and everything else. So that's the only difference. So you can create one truth table because they have the same inputs. The other one, you typically generate two truth tables because Z is only a function of Q's, not X. And then that would be the design for that. So, and this is what it shows over here. You see that X is going over here, whereas in the other one, on the board machine, see X is not going into the output generator. That's how you can tell this is a board machine. Okay. So, and the design pretty much is the same. The next step is, okay, what do we do with the unknown states? So here we have two flip-flops. So we know we are using, so we can say this is 0, 0, 0, 1, 1, 0. So we have a state 1, 1, which is unknown. That means due to surcharge, electricity, or whatever, we may jump to here. Maybe Q's become 1, 1. It's not part of the machine. So what are the options? Well, one option is like a toy. You can just, the kid has a little toy, bangs it on the table, it's not working, runs to mommy or daddy, and says on and off. Here you go. Okay, that would be the easy case. Now, the other one is, that would be like a toy, which you don't implement state, you just make it on and off. And in that case, we can use no cares. We put D and then but we put no cares. So everything you learn in the combinational circuit, truth tables, no cares, applies here as well. And everything else from here is straightforward. Okay, so that's one way. There's other options. There's fault tolerant. You can design it. I'm just skipping those. If you're interested, you can read about it, but just focusing on the main things. Fault tolerant, so that no matter uh, what happens, it will recover itself. It will not fail. Okay, that's called fault tolerant. We use more skates actually to do that. So we do the same thing. We find equations and then design it. In this case, this is the circuit for that. Immediately, you can see that it's kind of simplified a little bit. But remember, I said there are more and meaty depending on the problem. More output is always synchronized to the Q. It's always synchronized to the states. Mealy is synchronized to the states and the X. And the X. So if you switch the X, immediately it's going to change. So you can always design mealy and make it more by putting the output into a flip-flop. So flip-flop, the output, this is not depending on, this is not synchronized to the states this one is, right? Because X is going into here. If you change the X, output is going to change. But more, if you change the X, the output is not going to change unless you clock. There's no X in the Z. There are little differences, but we can always change, use the media machine and put a flip-flop and change it to the code. But main advantage is that some problems is much easier to design this way, meaty, than floor. And some problems are easier. That's just the way it is. The counter, if you want to build a counter, 0, 1, 2, 3, 4, 5, 4 is easier. That means if you define something like this, you can see that this is going to require you. And I'm going to give you an assignment. You can see the exact differences. Okay, I think the only thing that's left from here is counters, and we can talk about that next time. So I already assigned assignments. Take a look at it. If you have questions, just at least read it and bring it on Thursday. Okay.
When is it assigned to? Is it on Thursday?
I don't know. I don't remember.